All right, this is section 2.2 for Math 120, graphs of functions. Let's do an easy example where we're graphing a simple square root function. You might recognize this as a horizontal shift to the right, but let's go ahead and use this example to remind ourselves that what is the domain of this function? That's what we want to answer first. The domain is going to be all real numbers except for x values that make the inside of the square root negative. So what I would do here is I would take the inside of the square root, which is x minus 2, and set that greater than or equal to 0. Solving this inequality, I get x is greater than or equal to 2. That is the domain of this function. With this in mind, you can produce an xy chart with appropriate numbers. So starting with 2, then I'll go to 3, and then let's put a 6 into this function. So if we evaluate this particular function, we'll get the square root of 2 minus 2, which is 0. We'll get the square root of 3 minus 2, which is 1. And then we'll get the square root of 6 minus 2, which is 4. The square root of 1 is 1, and the square root of 4 is 2. So let's go ahead and plot these ordered pairs, 2, 0, 3, 1, and 6, 2. Connecting these with the square root curve gives me this graph. We can see that the domain is indeed all real numbers greater than or equal to 2. And this would be a good time to look at the range. The range is just your possible output values or your y values. So if we project this onto the y-axis, we're going to recognize that the range are all y values greater than or equal to 0. All right, the main focus of this section are piecewise functions. So what we have here is a function that has two expressions or two rules. We would say this is the first part and this is the second part. Since functions can only have one output per input, we're going to have to use only one of these for each input. So let's see, let's do the first one. F of negative 2 is the output when I plug negative 2 into x squared. I know that because negative 2, this input, is less than 0. So that tells me it's got to go into the x squared function. So if I square negative 2, I'll get 4. Let's do the next one. F of negative 1 is the output when negative 1 goes into x squared, which is 1. And I know that because negative 1, the input, is once again less than 0, which pushes me to the x squared function. Now look at the next input of 0. F of 0 is going to use the second function because 0 is equal to or greater than 0. So that means I'll take 0 plus 1, which is 1. F of 1 is going to be equal to 1 plus 1, which is 2. I'm plugging 1 into the second function because 1 is greater than 0. F of 2 is equal to 2 plus 1, and I'm plugging 2 into the second function as well. So here are 5 ordered pairs for this particular piecewise function. All right, let's make a table for and graph this piecewise function. So what I like to do is I like to make 2 parts to the table. One part is going to correspond to the first part of the function. So this will be the first part. So let's see, negative 1 is where a lot of things are happening. So I'm going to plug in negative 1, and then I'm going to plug in negative 3. Because those are both inputs for numbers less than negative 1. So if I plug negative 1 into the first function, I'll get 2 times negative 1 plus 3, which is 1, and then 2 times negative 3 plus 3, which is negative 3. I'm going to plot these 2 ordered pairs, negative 1, 1, and then negative 3, negative 3. It is a linear function, so it will be a straight line. And I can see that we do have a slope of 2, and it looks like it would cross the x-axis or the y-axis at 3. The reason why I have an open circle at negative 1, 1 is because of the inequality. It can't be equal to negative 1. All right, let's make a graph for the second part. For the second part, I'm going to plug in -1, and let's plug in 3. So when -1 goes into the second part, I'll get 3 minus -1, which is 4. And then when 3 goes into the second part, I'll get 3 minus 3, which is 0. I'm going to go ahead and graph -1, 4. I'm going to graph 3, 0, and connect those with a straight line. I'm using a closed circle here because of the equal to. If x is equal to -1, it would go into the second function. One thing we could do with this is recognize the domain and range. The domain is going to look at projecting this onto the x-axis. So notice that all numbers are accounted for. So the domain of this is going to be all real numbers. Looking at the range, we're going to project this onto the y-axis. So the highest y value is 4, and I can see a y value all the way down. So I would say the range, or y value, is less than or equal to 4. All right, here's another example of a 3-part piecewise function. So let's make a table for each of the parts. So the first part is just a constant function. The first part is simply -1. So I'm going to start with -1 as my input, and I'm going to do something less than that. Let's go -3. So no matter what I plug in there, as long as it's less than -1, my output will be -1. We will note here that we do have an open circle because of the less than sign. So plotting these two ordered pairs, -1, -1, and then -3, -1, produces the first part of this function. We will note that we need an open circle there at that -1, -1. The second part of this function is going to be y equals x. Let's plug in the 3 numbers, -1, 0, and 1, into the x column. And then the output will be the same number because it's the constant function of x. So -1, 0, and 1. So I'm going to graph that, and let's see, -1, -1, 0, 0, and 1, 1. So that is the linear function y equals x. So the third part of this looks like it's just a constant function again. I'm going to start with 1 and go to, let's plug in 3. So if I plug in 1 into this, the output is 1. If I plug 3 into here, the output is also 1. Let's make a note here that we do have an open circle at 1, 1 because of the inequality. So 1, 1 will have an open circle, and then 3, 1. And so here is a graph of the function. It turns out it is connected, it is continuous. Let's make a note for the range and domain. In this case, the domain is going to be all real numbers. There are no x values not accounted for. But look at the range. The range is a projection onto the y-axis. And so the range is going to be -1 is less than or equal to y is less than or equal to 1. All right, here's the final example. It's a 2-part piecewise function. Let's make a table first, with 2 sections. So the first section is a quadratic function, and some important things are happening around 2. So I'm going to plug in 2, and a number less than 2. Let's plug in 0. When I plug 2 into this quadratic function, I get 1 minus 2 squared, which is -3. If I plug 0 into this function, I'll get 1 minus 0 squared, which is 1. Let's make a note here that this ordered pair will be a solid circle because of the equal to. So 2, -3 is located there, and then, let's see, 0, 1 is located right here. With a quadratic function, it might be advantageous to go ahead and graph another point to get a better idea of what the graph looks like. Let's plug in -2. Let's see, that's going to be 1 minus -2 squared. That's going to be 1 minus 4, which is -3. So -2, -3 is again right here. So it's a parabola opening down, and it's going to end when x equals 2. So for the second part of this function, I have just a linear function. So let's start at 2. So let's plug in 2 and then 4. So 2 is going to have an open circle because of the inequality. And then let's see, that's the output's going to be 2, and when 4 goes into x, the output is also 4. So 2, 2 is located right there. The next ordered pair is 4, 4, which is right here. So this is going to be a linear function with a slope of 1, a y-intercept of 0, and here is my graph. Let's go ahead and find domain and range. The domain of this function is going to be all real numbers. Every x value is accounted for. And let's project this onto the y-axis to get the range. It looks like I have all the y values accounted for, except for this tiny interval above 0. So I would say the range are all values, let's see, negative infinity to 1. Now union that with 2 to infinity.